Hi everyone, I'm Jiawei from UT Austin. Now I will introduce our work at ITCS 2023, Consensus Division in an Arbitrary Ratio. This is a joint work with Paul Goldberg. Let's start with a classical problem called necklace splitting. So now suppose there are two thieves, A and B, and they steal a necklace. So suppose this necklace is a string, it's an open necklace. And on that necklace, there are n type of beads, and the ith type of beads has ai of them. Because we have two thieves, so now we just suppose ai is even number for all I. So this is example. So this is a string of beads, in total 8, and there are 3 types of them. So now our goal is to split this necklace. We want to cut this necklace in some places and give some pieces to the thief A and some pieces to thief B, such that it's an even split. Even split means each thief gets the same number of beads of each type. So here is an example. So we cut the necklace in 3 places, and we give the first and the third piece to thief A, second and fourth pieces to thief B. And you could check that the thief A gets 2 blue beads, 1 green beads, and 1 yellow beads. Thief B also gets 2 blue beads, 1 green beads, and 1 yellow beads. Okay, so it's an even split. And usually we want the number of cut to be as few as possible, because maybe, okay, the string on that necklace is also valuable. So by a topology theorem called Birch-Woolen theorem, you can show that n cuts always suffice. However, to find a solution with only n cuts is computationally hard. And a classical result showing that it's PPA complete. So we will introduce what is PPA this class later. So now imagine a scenario. One of the thieves said, I should get 2/3 of each type of beads because I did the most dangerous job. That's a quite natural scenario, right? So in our paper, we studied a natural generalization of the classical necklace splitting problem. We call it alpha imbalanced necklace splitting. Alpha is a ratio between 0 and 1. So the problem definition is mostly the same. The only difference is that now we want to cut the thick necklace and distribute pieces between thief A and thief B such that thief A gets alpha times AI of B's of type I. So the original necklace splitting problem is a special case with alpha equal to 0.5. So in this model, we may have some questions. So how many cuts are needed, especially in the worst case, okay, in this problem? So are n cuts still enough, right? And now what's the computational complexity of this problem? Is this problem still PP complete or belongs to some different class? Does it get easier or more difficult? A very closely related model called consensus halving. So consensus halving is a continuous generalization of necklace splitting. So instead of have n type of beads, now it's a continuous problem. So we have n probability measure function on the unit interval 0, 1. And we want to divide this interval 0, 1 into 2 sets of intervals such that the measure for each measure function, the set A contains about roughly half of the measure. So because it's a continuous problem, usually, okay, to define a computational problem, it's continuous problem, so we need some error term or approximation error. So when epsilon is inverse polynomial, you can show that consensus halving problem is equivalent to negative splitting. You could build reduction in both ways. And the consensus halving is also shown to be PPA complete. And it's PPA complete even for constant approximation. So note that the larger the approximation error is, the easier the problem gets. So it's even PPA complete for constant approximation, which is a very recent result. So naturally, we could also define an imbalanced version of the consensus halving problem. We call it alpha imbalanced consensus division. So we also have a ratio alpha between 0 and 1. And the problem is same as consensus halving. The only difference is that now we require, one set of intervals A contains alpha ratio, approximately alpha plus or minus epsilon fraction of the measure for each measure function. And interestingly, this model has been studied in a very old paper by Stromquist and Woodall. So they show that a general upper bound of 2n, so it means 2n cuts is always enough for any ratio alpha. And they also construct an example showing that for any irrational ratio alpha, in the worst case, 2n cuts are needed. So in this talk, and actually our paper, we focus on the imbalanced consensus division model, not the necklace splitting model. But we already tell you it's equivalent, actually. So all the results about rational ratio alpha in the consensus division could be applied to the imbalanced necklace splitting problem. Yeah, in the necklace splitting problem, you cannot define an irrational ratio alpha. So before I introduce our results, I want to give more background of the complexity side about complex class TFNP, PPA, and PPK. So TFNP is a class to contain all total NP search problem. So search problem means you want to find a solution, not only decide it's yes or no. And total means a solution always exists. And NP means you could verify whether a solution is a valid solution in polynomial time. So TFNP has many important subclasses and has been a very hot topic in the 5 years. And the subclass that is most relevant to our work is PPA. PPA is for the parity argument. So consider giving you a graph, and in that graph, there is a vertex of odd degree. Then there must be another vertex of odd degree. So this is a parity argument. So the computational problem of PPA is to give you a start vertex with odd degree. You should find the other one. So PPK is kind of mode K generalization of PPA. So to summarize, it's give you a bipartite graph, and I give you a start vertex V with the degree of V mod K is not 0. Then there must be another vertex V with degree mod K not equal to 0. So it's kind of a mode K argument. So basically, by definition, PPA is PPA2. And another property I want to know is that it's believed that for two different prime P1 and P2, PPA P1 and PPA P2 are not comparable. Means, for example, PPA2 doesn't contain PPA3, and PPA3 also doesn't contain PPA2. And unlike PPA has some natural complete problem like necklace splitting, PPK now only have very few natural complete problems. Another related problem is called consensus K division. So consensus K division is generalized consensus halving in a different way. So our imbalanced consensus division is, now we still have two thieves, but we don't want 1/2 split. We want to split to alpha and 1 minus alpha. But in the class K division, now we have K thief. And we want to divide into a K part, and each part have 1 over K. And in this case, you could show that in the worst case, n minus 1 times n cos is enough. And this problem has been studied before. It has been shown that this problem is in PPK by term reduction. And in particular, if K is a power of prime, if K equal to P to the R for prime P, then this problem is in PPP, which relies on the property of the PPK class. And this problem is conjectured to be PPK complete for prime K. So this is a major open problem in this field. And you could similarly define K negative splitting. So now we are ready to introduce our results. So first, from the combinatoric side, we show how many cuts you need to guarantee a solution. So first is a lower bound. So for any rational ratio alpha, we assume alpha equal to L over K, then roughly 2 times K minus 1 over K times n cuts are needed in the worst case. So to be more clear, here is a visualization. So here I plot the lower bound for all rational number with denominator smaller than 50, and they form a quite beautiful pattern. So for example, this dot, alpha equal to 1 over 2 is a classical halving or negative splitting problem. And in this case, the bound is n. This is a previous result. And for any other alpha, we show that there is a bound between n and 2n. And actually, this pattern is identical to an upside-down Thomius function. And recall that the Stromacast and Woodall show that for any irrational alpha, the bound is 2n, so above all the rational numbers. And this lower bound is proved by a pure ad hoc construction. So also give some upper bound. So the first part, upper bound, showing that for a large subset of rational numbers, we have the same upper bound. So we show that for a large subset Q star, for any alpha in Q star, we get matching lower bound and upper bound. And it's difficult to give an explicit form about Q star or short description. But I can tell you Q star contains all the fractions of form 1 over K. And it also contains a lot more fractions. And for any other rational alpha, we give an upper bound of C alpha times n, where C alpha is constant, strictly smaller than 2. So we still improve upon previous upper bound of 2n. So one numerical example is that for alpha equal to 2 over 5, our upper bound is 9 over 5 times n, while the lower bound is 8 over 5 times n. So this upper bound is from a reduction from the consensus K division. So for example, to get upper bound for 1 over 3 imbalanced consensus division, we use a reduction from consensus 3 division. So this type of reduction is inspired also by the original Stromacast and Woodall paper. And we believe the lower bound seems to be tight and the upper bound is not optimal. So it's not only the pattern of lower bound looks prettier. If you read the proof of upper bound, it feels a kind of weak, especially for the number not in Q star. It looks suboptimal. So now we introduce our result about the complexity part. So first, for the same subset Q star of rational set alpha, So we show that finding the solution, okay, using this number cuts. So this number is both the lower bound and upper bound. So this combinatorial problem lies in PBK under Turing induction. And in particular, if K is a power of prime, okay, then this problem lies in PBP for the prime P. So for example, solving 1/3 imbalanced consist division with 4/3 times n cuts lies in PBA3. So this theorem 3 is basically from the same reduction to get the upper bound. We use same reduction from the consist K division. And we also get a kind of intriguing complex result when you give more cuts than necessary. So usually when we study next splitting cuts halving, we consider, okay, what's the minimum number of cuts that makes this problem total? But it's natural that if you give more cuts, then the problem maybe becomes easier. And here is our result. So for any alpha and any prime P, we show that finding an inverse polynomial approximate solution using, okay, this is still a constant times n cuts is in PPP. Okay, this is a constant only related to n. So here is some example. So for any alpha, we show that the alpha imbalanced consist division with 2 n cuts is in PPA. Okay, and for the consist halving problem, where alpha is 0.5, okay, if you give 8 n cuts, then this problem is in PPA3 now. So previously, I said it's believed that PPA and PPA is PPA2, PPA is not comparable with PPA3. So if with 8 n cuts, this problem is not only in PPA, now it's also in PPA3. So it's a strong evidence this problem with 8 n cuts becomes strictly easier. And so this kind of result, we also have this kind of result previously. So people have shown that for consist halving, it's still PPA complete with n plus n to the 1 minus delta cuts. So delta is any constant. Yeah, but this is still smaller than like 1.001 n, right? So it doesn't give like linearly more cuts. And on the upper bound, on the algorithm side, people have shown that if you give n log n cuts, then finding an inverse polynomial approximations solution is in P. Here is a visualization of the situation for solving consist halving with inverse polynomial approximation. Okay, so if you only give n minus 1 cuts, so this problem is not even total. The solution with n minus 1 cuts not always exists. This problem is NP complete. And once you give n cuts, this problem is become in PPA. And actually, for n cuts or even n plus n to the 0.999 cuts, this problem is still PPA complete. Okay, and our paper show that okay, once you give 8 n cuts, then this problem further belongs to PPA3. And you can also plug 5 into this bound, and you will get with 12 n cuts, this problem further becomes in PPA5. And if you give too much cuts, like n log n cuts, then this problem is in P. So we believe this bound is not optimal, but it does give you a sense that what's happening when you get more cuts. And a corollary is, okay, for any prime P, if you want to find an inverse polynomial approximation solution for the constant K division problem, okay, then you still need about a constant times n cuts. That is in P. Okay, this bound is now related to K and P, but still a constant. And note that this bound is basically K minus 1 multiply the previous bound. And actually, this corollary is proved by, okay, to solve a constant K division, you could solve it by calling the imbalanced consistent division k minus 1 times. Okay. You start by calling a 1 over k imbalanced consistent division. So now you carve out one part of 1 over k of shear. And then you apply the 1 over k minus 1 imbalanced consistent division on the remaining part. Okay, then you again carve out 1 over k shear in the original instance, and you do it k minus 1 times. And our last result is showing that, so for any alpha, find a solution using the minimum number of cuts for each specific instance is NP hard. Okay, so now this problem is not a TFNP problem because for each specific instance, okay, we want to find a solution with the minimum number of cuts. So this is reduced from the exactly once reset problem. So exactly once reset means, okay, you want to get an assignment such that exactly one letter is satisfied in each clause. And this is similar to this reduction is similar to the construction of the lower bound. And this result is not very surprising because in the previous paper, people already showed that decide whether a halving problem instance could be solved with n-1 cuts is NP hard. So our result is a generalization of previous results. Yeah, but I still want to say our proof is very different. So in the previous paper, their reduction is from the set problem, and a main tool in the reduction is to use a problem called generalized circuit problem, J-circuit. So J-circuit is a tool problem constructed usually for reduction in PPAD. But our reduction doesn't use this J-circuit. It's completely different. Finally, we will introduce some open problems left in this paper. So the first one is to close the gap between our current lower bound and upper bound for the number of cuts you needed in the worst case. So our conjecture is that our lower bound is tight and upper bound is suboptimal. And maybe this could be proved by some clever trick to use a mode P variant of the Bernoulli theorem, or some ad hoc approach. Yeah, we have tried some ad hoc approach, but we failed. But maybe we missed some very simple and clever ad hoc proof. And the second open problem is to improve our results on the complexity side. So recall that we only showed the in PPK result for that subset Q star, right? Because only for number in Q star, we have matching lower bound and upper bound. So maybe to improve the complexity result, we may first have to improve in the upper bound. And once we improve the upper bound, we may have a very high chance to directly also improve our complexity results. So our conjecture is about, okay, solving L over K imbalanced consistent division with 2 times K minus 1 over K times N cuts. This is a conjecture bound for both lower bound and upper bound. This problem is in the true enclosure of PK. And conjecture 3 is for the phenomenon, okay, the problem gets easier when you get more cuts than necessary. And we have a very bold conjecture. Solving alpha imbalanced consistent division with 2 N cuts is already enough to put it in the intersection of all PPK cuts. And the last open problem is to prove any PPK hardness results. So because now we kind of lack natural complete problem for class PPK. So for example, we conjecture that solving L over K imbalanced consistent division problem, okay, with this number of cuts is PPK complete for any prime K. So it only depends on the denominator, not the numerator. And another motivation for this open problem is, okay, because we already built some reduction from the consist K divariant problem to the alpha imbalanced consist divariant problem. So for example, once you prove the 1/3 imbalanced consist divariant problem is PPA3 complete, then you directly get consist 3 division is also PPA3 complete. And the latter one is a major open problem in this field. And advantages of attacking this problem is that in our problem, we only have 2 thieves, right? So it may be easier to design gadget with only 2 labels. Okay, with only 2 labels, when you design gadgets, the label will alternate, and which always be the case in previous paper when showing the PPA completeness for negative splitting and consist halving. Yeah, but if you want to directly design gadget like for consist 3 division, then it's trickier because there you have 3 labels. And but maybe it's also not easy because now you get more cuts. So what that means is, okay, like for 1/3 imbalanced consist divariant, to make it total, you have to have 4/3 times n cuts. Okay, so now for each measure function or for each type of beats, you have more than 1 cut. So maybe you have to design like a gadget with 3 measure function and 4 cuts. And we found this is also tricky to deal with. So this is our talk, and here's a reference.